Hello all, welcome to my channel. In this video, I will explain how to use simplex method to solve a linear programming problem by two-phase method. I have already made a video to solve this problem, but we will solve the minimization case as a maximization problem. The given problem is a minimization type of problem. Minimize z is equal to 5x1 plus 3x2 subjected to three constraints. The first constraint is 2x1 plus 4x2 is less than or equal to 12. The second constraint is 2x1 plus 2x2 is equal to 10. And the third constraint is 5x1 plus 2x2 is greater than or equal to 10. And the non-negativity restrictions, that is x1 and x2, both decision variables are greater than or equal to 0. First, what will we do is we will convert this minimization problem into maximization problem. And how do we do that? We do it simply by multiplying the objective function by -1. So this minimization type objective function is now changed to maximization type of objective function. And instead of z, we have written here z dash, and the right hand side, which is plus 5x1 plus 3x2 has become minus 5x1 minus 3x2. And there is no change in the constraints or non-negativity restrictions. Now the next step is to convert the maximization problem into the standard form. So how do we do that? In order to convert it into standard form, I have already made a video. I will share the link in the description, or you can also check the I button at the top to understand how to convert the given problem into the standard form. So here we have first constraint as less than or equal to, second constraint as equal to, and the third constraint as greater than or equal to. So the first constraint, that is less than or equal to, will be converted into equal to by adding the slack variable s1. Then the second constraint is equal to, so we have to add artificial variable in the second constraint, and we get 2x1 plus 2x2 plus artificial variable a1 equal to 10. In the third constraint, it is a greater than or equal to sign. That's why we have to add surplus variable. Now, if we add surplus variable here, s2 will be equal to minus 10 if we put x1 and x2 as 0. That's why we have to add artificial variable in this third constraint as well. So the non-negativity restrictions now become x1, x2, s1, s2, and a1, a2 all are greater than or equal to 0. And the objective function becomes maximize z dash is equal to minus 5x1 minus 3x2 plus 0s1 plus 0s2 coefficients of slack and surplus variable minus a1 minus a2 coefficient of artificial variable is -1 in both the cases, as it is a maximization problem. And the initial basic feasible solution can now be found as, considering x1 and x2 as 0, we get s1 is equal to 12. So s1 is equal to 12. Again, here x1, x2 is 0, so a1 equal to 10. a1 equal to 10. And here x1, x2 is equal to 0 and s2 is also equal to 0. So we get a2 equal to also equal to 10. So this x1, x2 and s2, for which the values are 0 in the initial basic feasible solution, are called as non-basic variable, because this variable will not be in the solution initially. So these are called as the non-basic variables. Whereas the variables S1, A1 and A2, which are giving us the solution of this LP problem, will be considered as the basic variables. So the maximization problem is written in the standard form. So the maximization problem is written in the standard form as it is displayed here on the right hand side of the top right corner. Now phase 1 is to convert this maximization problem into phase 1 problem. How do we do that? For that, we will write this problem as it is, and we will make the coefficient of x1, x2 also equal to 0. So we will have coefficient only of a1 and a2, and the objective function looks like this: 0x1 plus 0x2 plus 0s1 plus 0s2 minus a1 minus a2. Now from this we will form a matrix which looks like this, and we call it as basic tableau. Again, how to form this matrix? I have explained it in the video. You can check the I button, or I will also put the link in the description. Here we will first find ZJ value as -7, -4, 0, 1, -1, and -1. How do we get ZJ value? 0 into 2, that is 0, plus -1 into 2 is -2, 0 minus 2 is -2, and -1 into 5 is equal to -5. So -2 minus 5 is -7. Basically, it is multiplying these values by each column, and we get the ZJ value. Then CJ values are written at the top. So CJ minus ZJ will give us 7, 4, 0, -1, 0, and 0. Now, as we are solving the maximization problem, we will find the maximum value in the CJ minus ZJ column. And this value of 7 is the maximum value. That's why this column of x1 becomes the key column. Now, what is the importance of key column? The element x1, which is in the key column, will now enter into the solution. But x1 will take whose place? That we have to determine. That can be determined by finding the ratio, and ratio is equal to the solution column divided by the x1 column. After calculating the ratio, we get -2 as the least value. So this row of A2 will become the key row. What does this key row indicates? The key row indicates that this variable A2 will now leave the solution, and the intersection of key column and key row is called as the key element. This 5 is the key element here. Now, what is the importance of key element? In order to find the first iteration, this key element should be made 1, and the other elements of the key column should be made 0. That means this 2 should be made 0, this 2 should be made 0, and this 5 should be made 1. And it is calculated here. So in order to make this 5 as 1, we will divide this row, that is the old R3 row, by 5. The same thing is written here. So R3 new equal to R3 old divided by 5, and we get these entities. Similarly, we'll follow the row operation for making this 2 as 0, and the operation is R1 new equal to R1 old minus 2 times R3 new. And finally, for making this 2 as 0, will follow R2 new equal to R2 old minus 2 into R3 new. So these are the elements of the matrix of iteration 1, which we have written like this. Again, as explained, we'll find ZJ value and CJ minus ZJ value. Note here that there is no entry made in the column A2 because A2 has left the solution, and we do not want A2 to enter the solution again. So we have left this entries in the column A2 as blank. Now in the CJ minus ZJ value, we have 6 by 5 as the maximum value, So this column, that is x2 column, will become the key column. It means x2 will now enter into the solution, and who will leave the solution? How do you find that? For that, we divide the solution by x2 column. So 8 divided by 16 by 5, 6 divided by 6 by 5, and 2 divided by 2 by 5. And we get the ratio column as like this. Now, if you look at the ratio column, the first row, that is the S1 row, is having the least value of the ratio, that is 5 by 2. It means S1 will leave the solution and X2 will enter the solution. The key element here is 16 by 5. And what is the importance of key element? I have told you just now, the key element should be made 1 in the next iteration, and the other values and the other entries in the key column should be made 0. So let us do that. So here you can see key element 16 by 5 is made 1 by this row operation, that is R1 new equal to R1 old into 5 by 16. Similarly, the second row, the entry 6 by 5 is made 0 by using the row operation R2 new equal to R2 old minus 6 by 5 R1 new. And finally, the value 2 by 5 is made 0 by using the row operation R3 new equal to R3 old minus 2 by 5 R1 new. So this forms the table for the second iteration, which is written like this. Now, if you see in this table, A2 column is having no entry since it has already left the solution. You may also skip to write the A2 column hereafter. If you find the Cj minus Zj values, so below x1 we have 0, below x2 we have 0. Otherwise also, since x1 and x2 are in the solution, the Cj minus Zj value for x1 and x2 should always be 0 because x1 and x2 both are in the solution. Similarly, A1 in the solution, so Cj minus Zj value below A1 should also be 0. Now we are left with S1, which is showing negative value, which cannot enter the solution. So S1 cannot enter the solution. So the only value that is positive is 1 by 4, which belongs to S2. So S2 becomes the key column and S2 will now enter in the solution. Now we have to decide the leaving variable. How do you find that? We divide solution column by key column values and we get 12 as the minimum value and A1 is now the variable which will leave the solution and S2 will enter the solution, and the key element here is 1 by 4. So again, performing the row operations to make this 1 by 4 as 1, this 1 by 8 as 0, and minus 1 by 4 as 0 in this way. So here we have made this 1 by 4 as 1 by performing this row operation. Then by performing another row operation for making 1 by 8 as 0 in the form of R1 new equal to R1 old minus R2 new into 1 by 8. And finally, to make this minus 1 by 4 of the R3 old row as 0 by using the equation R3 new equal to R3 old plus R2 new into 1 by 4. And putting these values for iteration 3 this way, So as there are no artificial variables in the basis, so phase 1 ends. And now we can start with phase 2. This table now becomes as the table for phase 2 with one change. What that change will be? X1 and X2 will have its coefficient from the objective function, which will also for phase 2 as like this. The objective function is now maximize z dash is equal to minus 5x1 minus 3x2 plus 0s1 plus 0s2. So for x1 we will write minus 5 as the coefficient here in the Cj row, and for x2 we will write minus 3 as the coefficient here in the Cj row. And these values are obtained from the earlier table. Same values we have copied there. Now the next step is to find the value of Zj and then Cj minus Zj, which gives us 0, 0 and 0 under x1, x2 and s2 column. So we can check s1 is in basic, yes. x2 is in basic, yes. And since s2 is also equal to 0 in Cj minus Zj row, s2 should also be in the basic. So s2 is also in the basic. And only S1 is left, which is not in the basic, which can enter the solution. But as S1 is equal to minus 1, and we are solving a maximization problem, S1 cannot enter the solution. So all the entries under Cj minus Zj are negative or 0. And there is no positive value under Cj minus Zj row. So since it is a maximization problem, there is no entering variable, positive variable. Thus, the optimum solution has been reached or obtained, and the iteration stops here. So we have the final answer as x1 is equal to 4. We'll see the value in the solution column. X1 equal to 4, x2 is equal to 1, and s2 is equal to 12. We do not have S1 in the solution. It means S1 is equal to 0. And S1 is non-basic variable. This is the answer. X1 is equal to 4, X2 is equal to 1, S1 equal to 0, and S2 is equal to 12. Therefore, Z dash will be equal to minus 5x1 minus 3x2 plus 0s1 plus 0s2. Substitute the value of x1 and x2, we get minus 5 into 4 minus 3 into 1, that is minus 23. Now we have to convert back the maximization problem into a minimization problem. How do we do that? Z is equal to negative of Z dash. So minimize Z equal to negative of maximize Z dash. So that is equal to negative of maximize Z dash. What is the value? Minus 23. Thus, the value of Z is 23. This way, we can solve the minimization problem by two-phase method by converting the problem into maximization problem. Thanks for watching. If you have liked the video, hit the like button and subscribe to my channel.